Okay, so here is the second of the two types of questions or that are very common in calculus. The first one being derivatives, which are slopes. The second one now being integrals. So an integral, okay, is simply finding the area under the curve. Right? So the area can be found by adding slices that approach a width of 0. So if we go over to our picture here, basically what's happening is you create this delta x, right? These nicely shaped rectangles, and essentially you're going to figure out the areas, for each one of these, and then really integrals in this method are what we consider to be approximations, okay? Because you can see some parts of the graph are above, some parts of the graph are below. Well, ultimately what you're going to do is make these little areas even smaller every time. So if I just kind of like do something like this, change that one area into 4 areas, and do the same thing. So my delta x is going to approach, right, a 0 point, which means you're going to have an infinite amount of areas under the curve. All right, and that's the goal of an integral, is somehow get to this infinite number of areas under the curve. Okay, so the integral notation, right, or more specifically, the indefinite integral, right, which just gives us a general form. Okay, looks something like this. This is our integral notation. They call it like a fancy S. You're going to have the function. Okay, it's more specifically, it's the derivative of the function, and then dx. So you can see this dx notation looks like delta x. And so what this does, it sums all those little integral, or those little areas, okay, to a point where now it's an infinite amount. Okay, so this is our, what we call the integrand, right? And then x is the variable of integration. All right. So that's what we're integrating with respect to. So all of our function, right, has to be in terms of x. If there's anything other than x, right, we treat that as a constant. So if I had like a z, if I had z plus x, and I'm taking the integral with respect to x, z is being treated as just a constant value. It doesn't matter what it is. It could be a function in itself, but because it's not with respect to x, then we're just treating it as a constant value. Okay. Now in physics, we're only going to use a certain type of integral, because what we're going to do is we're going to use what is called a definite integral, as opposed to what I just wrote. That's an indefinite integral. We're going to find a definite integral. So where indefinite integrals deal with general, right? Definite integrals will find specific areas now. So this is where we actually return numerical values. Okay. And so we're going to get an actual number here, because we're going to have a set specific. We're going to have an interval through which we're going to find the area under. So we know exactly what we're going to do. So, and I'll erase that just so we can, draw the picture again. So like, let's say this is my A and this is my B. So I'm not looking for anything below A or above B. I'm just looking for the area here. Okay. That's when I find the integral using my two intervals. Okay, or my interval. That's how I can find the specific number, as opposed to the indefinite. I'm finding just the general equation. So the notation looks a little bit different. It's still the kind of the same idea. All right, so f of x is f prime of x, the integral of f prime of x dx. But now what I'm going to do is I'm going to have these upper and lower limits, right? So this is my upper limit, or sorry, this is my lower limit. And this is my upper limit. Now, what that does is, once I find the function, I'm going to do f of a, right? or sorry, f of b was my upper limit, minus f of a. And that's going to produce a number, and that number is my area. Okay, so when you do a definite integral, now you actually find a specific number, a specific area that is associated on that interval. Okay. Now, again, just like with derivatives, we only have a handful of rules that we have to really worry about in physics. So the first one is the constant rule. So if I take the integral of a constant, okay, well, the only thing that happens is it's going to be the constant times the variable. Okay. So the way to think of it is that integrals and derivatives are like addition and subtraction. If I have one of them and I want to get rid of it, I do the other one. So really what that was is like, if this was my constant number, that means my original function started out to be just linear. Okay. Now, if we had an upper limit and a lower limit, well, you would see this kind of notation, which means you're going to evaluate this function from a to b. So you're just going to do cb minus ca. And if you have numbers there, and we'll do some specific examples here in a second, okay, you would just kind of subtract this multiplication and that multiplication. Okay. Now, the general power rule. So if I'm doing the integral of x to the n dx, okay, it's a little bit different than when we did it with derivatives, where we brought it down and we subtracted one. Integrals actually adds an exponent, okay? So what happens is, out front, if you want to say, will become a fraction. And again, n is our original exponent. Right, so we're going to do 1 divided by n plus 1, and then we're going to multiply that by x to the n plus 1. Now, in calculus, like if you're sitting in a calculus course, you will have to write this plus c, where this is just a constant that you can find by using some initial conditions, right? We saw that in one of the homework problems where it added the plus 8, I think was the value, and you had to go back and use the actual function or the initial conditions provided to you in the problem so that you can figure out what plus c is. Okay, but this is our basic rule: 1 over n plus 1 times x to the n plus 1. And you could write this x to the n plus 1 over the n plus 1 if it's easier for you. But you understand there will be a fraction that pops out. So that part, this part right here, is a number. Okay, and then the sum and difference rule. I mean, it's essentially the same thing as what we did before with the derivatives, where we can break this apart. So it's like we do the integral of z dx plus or minus the integral of y dx. Again, as you get used to these, you're going to do them in one shot. You're not going to break them up into 2 separate, 3 separate, 4 separate. Okay, but again, I like to say, crawl before you run, right? So you have to crawl, then you walk, and then you run. So this is kind of like the crawl step. But as you get used to it, you're going to go right into running, and you're just going to do them, right? Okay. So if we just have a couple examples here. So we're going to find the integral of the following on the interval from 0 to 1, right? So we're going to find the area, which is what we're really finding, right? So we're going to find the area of the function provided on our interval from 0 to 1. So 0 would be A, 1 would be B. Okay. So if I write that notation, I'm going to say, f of x is x cubed dx, and I'm going to evaluate this from 0 to 1. Okay. Well, the first thing I need to do is figure out the integral. Okay. So I'm going to use my power rule. So I'm going to do 1 over 3 plus 1 times x to the 3 plus 1. Okay, that's my power rule. And then I'm going to evaluate that from 0 to 1. And that's what this line means evaluate. So if I simplify this, I got 1/4 x to the 4th evaluated from 0 to 1. And so I just simply put in 1/4 times 1 to the 4th minus 1/4 times 0 to the 4th. And a lot of times when you have 0, yes, that's what happens. That whole second term there goes away. So for x cubed on the interval from 0 to 4, right? In fact, this is equal, it's going to be 1/4, or in physics, we want decimals, so it'll be 0.25, okay? Now, here's how it changes if we have a constant in front, right? We still do the same thing. So we're going to do the integral of 5x cubed, evaluated from 0 to 1 of dx. Now, because we're doing definite integrals, we don't have to write that plus c I showed you earlier. That's because we're finding specific numbers, and the other one is just general values, okay? So again, I follow my rules. I'm going to have 5, right, times x to the 4th over 4, right? Because it's essentially this integral right here, right, that from before, okay? And we're going to evaluate that from 0 to 1. Now, you can clean up here. You can say 5/4 x to the 4th, evaluated from 0 to 1. So I got 5/4 times 1 to the 4th minus 5/4 times 0 to the 4th, right? And so that gives me, I'll write it right above it here in a different color, around our room, right? An area of 5/4, right? Again, so if you plotted this function 5x cubed and you drew an area from 0 to 1, that area would be equal to 5/4. Okay. Now we have one that has got a constant here, so we would have the integral of 5x cubed plus 2 dx from 0 to 1, right? And then, so what we're going to do is, again, so it'll be this integral, 5/4 x to the 4th. Now, you can break it apart like we do in our sum and difference rule here. I think I actually have that backwards. I think it's 0, and 0 goes on the bottom. I apologize for that. So our 0 and our 1, right? Think upper, lower. Sorry about that. 0, 1. So if I quickly go up here where I did my, definite integral, this would be your lower limit. I apologize for that, right? And that would be your upper limit. So upper, lower, right? So lower, upper, lower, upper. But this is still right. It's still always your upper minus your lower. I didn't mess that part up, okay? So I apologize for that little confusion there, okay? And so now because we have the constant, we're going to add the x to it, right? And we're going to evaluate that from 0 to 1. Okay, so we're going to do 5/4 times 1 to the 4th plus 2 times 1 minus, and this is why 0 is great to have as your other limit, because it's just going to be minus 0. So your answer is really just going to come from your first half here. So you got 5/4 plus 2, which ends up being 9/4. So you can see as I add parts to this, my area gets bigger, right? So here my value is 1. I was 1/4. Here it's 5, so it becomes 5/4. Here I'm adding in this part to it. No, that's 13/4. Yeah, 2 is 8/4. Sorry. Again, right? I guess I am human. So this would be 13/4, right? So you can, because this is 8/4, right, in terms of fourths. Okay. Now we got a little bit longer, and this is where, right, I'm just going to kind of shorten my work here. I'm going to take the integral of this whole thing. So we're going to get that 5x to the 4th. Okay, minus, now squared becomes cubed, right? So I'm going to have 10x cubed over 3, because I got 1/3 x cubed is the integral of x squared. And then I'm going to have minus x squared, because this becomes 2x squared over 2, right? Well, those cancel out, leaving just x squared. And then I've got my constant, and I'm going to evaluate that from 0 to 1. Got a little too close to the edge, right? So it's going to go to 0. Again, a little close to the edge. this one went a lot further this time. So it's going to be the 1, right? Again, the great thing about this whole thing is that this set, you know, my minus upper limit part is just going to be 0. So we're going to have 5 times 1 to the 4th over 4 minus 10 to the 1 cubed over 3 minus 1 squared plus 4 times 1, right? And so it's going to be 5/4 minus 10/3 minus 1 plus 4. I'm going to grab my calculator real quick. Enter all that in. And that's going to be 11/12. Okay. So this area is, even though it's, you got bigger, it's going to do a little bit crazier stuff in there. Okay. And you also have to make sure that there's no turning point inside that area, because if it is, then you have to kind of go from one part, you know, figure out the turning point. So your lower limit, you would have 2 integrals. You have one at the low end, one at, you know, so lower limit to turning point to upper limit. Okay, if it turns inside of that interval. Okay. All right. So now, where do we see this in physics? Well, that stack that we talked about, but now we're going to kind of go the other way. So if I have an acceleration time graph, right, which tells me that velocity is so v of t is the integral of a of t dt. So I'm going to go from horizontal line, it's going to turn into a slope line, right, my vt. And then my position, my x of t, right, is the integral of v of t, which then becomes parabola. Okay, so you have to remember, this is constant, right? This is linear, and now this is parabolic. Right? So constant becomes a line becomes a parabola. Okay. So if I'm going, in the previous video, I started my parabola and I went down to my constant. Here I'm going to start at my constant and work my way up to the parabola. Okay. Now another area where you do see integrals, and we're going to run into it, is a concept called work. So work done is the area under a force versus position graph. Okay. And so this here is force, not function. Okay. And so this is, so if I take a force versus position graph and I have a function that looks like this, right? The area under the curve is the amount of work done on that object. And what happens is you see a lot with springs. In fact, that's going to be our example in this. Okay, it's going to ask you to find the work done on a spring, stretching it from one point to another, where you have to do that. All right, so if we just take a quick look at this example problem. So it says the amount of force that is exerted on a spring is given by the function f of x equals 2x squared minus 3x plus 4. And I've put in something with a k, but I changed the problem, so we don't have to worry about this. Okay. K is the force constant, and so essentially what we're doing is x is how far the spring is stretched, and so how much work is done on the spring and stretching it from 2 to 8 meters. Okay, so the amount of work done is the integral, in this case from 2 to 8, of our function, so 2x cubed or 2x squared minus 3x plus 4 dx. Okay. All right, and so then we're going to do our integral. So this becomes cubic, so it's going to be 2/3 times x cubed minus, this becomes a squared, so it's going to be 3/2 x squared, and then this becomes a line of 4x. And we're going to evaluate that from 2 to 8. And so when you get something like this, this becomes just a little bit more lengthy, right? Our lower limit is not 0. So now we're just going to plug in our values. We're going to evaluate when it's equal to 8. So we got 2/3 times 8 cubed times 3/2 times 8 squared plus 4 times 8. All right, that's the first part. And then we're going to subtract that. We're going to subtract 2/3 times 2 cubed minus 3/2 times 2 squared plus 4 times 2. All right. And so my recommendation here is kind of break this apart. All right, so the amount of work done. So we're going to do 2/3 times 8 cubed. And we'll call it 341 minus 3/2 times 8 squared, 96, plus 32. I can do that in my head. Minus 2/3 times 2 cubed. So it's 5.3 minus 3/2 times 2 squared, 6, plus 4 times 2 is 8. Okay, and so we got 341 minus 96 plus 32. So work is going to be 277 minus 5.3 minus 6 plus 8, 7.3. And so we do 277 minus 7.3, and we get, call it approximately 270 joules worth of work in doing that. Okay. In fact, you will see this formula from before in the integral section, right, of calculus. You see this formula pop up because it's just another area that's not related to motion that uses integrals. Okay, so in the next video, I'll address the unit vectors and vector notation and so forth, and how it's related to physics, especially with the position, velocity, and acceleration vectors.